Okay, right. So, uh, this is your week 4 problem solving session. So, yeah, you can also let me know if anything that is not going right with this course, something you are struggling or something you are not finding clear at any point, whether in assignments or or anywhere in any other resources of this course. Like first of all, makes you make you can make sure that you are able to access all the resources provided in this registered. So yeah, so I think we are already halfway through this course. So I hope you are able to catch things properly. So if not, so please feel free to clear your problems here without any hesitation. Uh, So today uh, uh, we were planning to discuss about quantum information. So if you would see your week 4 and week 5, there's some discussion already on quantum information. Particularly if you see your week 5, and we'll see there will be some more topics in week 4, like the nuclear magnetic resonances, time dependent Hamiltonians in quantum dynamics. Those things maybe probably we want to be able to cover right here today. So we'll try to go through some important problems of those topics maybe from the next week. And with today we'll try to stick with quantum information. So it is very interesting topic that you would find in advanced quantum mechanics. So that is quantum information. So if you see, uh, like I mean, it is the foundation of quantum computing. Like you know, the if you know about information, classical information, which we like study using the notion of bits, which are essentially the basics of classical computing. So just like that, we have quantum information here. We will be seeing the idea of qubits, which are the basic the I mean the information that you will be dealing when we talk about quantum computers. So so when we are talking about quantum information, so these qubits, so they bring about a lot of other different phenomena, and upon exploiting them, we have a great amount of like technological benefits. So we'll also try to see some of them, like particularly quantum teleportation. There are quantum key distributions, which are something very much like the advanced version of classical encryption. So all this uses or all this uh, uh, some incredible advantages we can have are just manifesting quantum principles and quantum phenomena. And also quantum information, I mean, it's not just we'll find within I mean, we will not just going to limit our understanding within the application of quantum information or the information age. What I mean to say, you would see, like for example, the phenomenon like quantum entanglement. So it stretches to all possible domains, even in biology. So there are, whenever we deal with any quantum system at any uh, emergent level of science, whether it's even if it's biology or chemistry. So still there we will be seeing this quantum phenomena. So wherever we go to the quantum realm, whether it's in the information system that we are talking about, like the information technology, which will try to see how qubits are the fundamental to this subject. And So there we'll see this how this new phenomena like emerges, and also we can same way we can also see them in other domains as well. So when we go to that quantum realm, whether it's the field of biology or even chemistry, so it's everywhere when we are in the quantum regime. So we will have this very uh, intriguing phenomena. So yeah, uh, okay. So first we can try to see what is entanglement. So this is the like we can say from here, like we can all the different uh, new advantages that which we can have from quantum information, which I was just mentioning moments ago. So it all stitches to this phenomena known as quantum entanglement. So yeah, right. So okay, so what is this entanglement? So just a some background of idea which we can have before understanding what is entanglement. What happens, like if we have let's say, if you have two or more quantum systems, and they are described by two Hilbert spaces. Let's say we have two quantum systems, and they are associated with two Hilbert spaces. So for example, you can think of like two quantum harmonic oscillators. Like you have one harmonic oscillator. Let's say you have uh, two quantum harmonic oscillators. uh, you have two quantum harmonic oscillators. So you will denote one quantum harmonic oscillator with n1 notation, and the other with n2. So this n1 is basically one the number states in quantum in the I mean the number states of the number eigenstates, you can say, for this harmonic oscillator. So for first quantum system, you have one set of number states, and for the other you have other set of quantum number states. They are the eigenstates of that harmonic oscillator system. And if you see that this number states, like it is particularly this number states spans the Hilbert space one, and you will see it will span the Hilbert space two. So this is where you have two different Hilbert spaces, and when we combine this system, we have a composite system, or basically we get a new, when if we combine like if we combine these systems, like we will have, so we do something this kind of operation, tensor product. So we'll see that like this uh, um, will be in a in an extended Hilbert space. So now your Hilbert space is not just H1 or H2. It's even much bigger than that, because you we are seeing a quantum system which is composed of two harmonic oscillators. And they are given as this tensor product. If we see their quantum states, then they would be denoted by this n1 tensor product n2, and they would be living inside this extended Hilbert space. So just like that, like if we have also spin state, like we know spin state is a very uh, like a very basic system, which is and this is what something we will be thoroughly like exploiting it throughout our discussion today, because the spin states are one of very suitable accessory for us to use it for information like processing or something like relevant that we have seen in classical information as well. Like for example, we use bits which are like either zeros or ones. So even quantum states, like if we talk about spin states, so they also come, they also appear as up state or down state. And if we uh, take multiple spin half systems, so we'll have some composite system. And then there are something called entangled states, and using that, like we will have more like, I mean, using them, there are some even more possibilities of 0 and 1. Like, I mean, if we just take the linear superposition, so we get superposition states. So these are not really like ordinary 0 or 1 state, like classically how we know. So even here we have linear superposition. So that is why we'll slightly treat them as different kind of bits, rather classical bits. So that is what we'll be calling them as qubits. So yeah, like even in spin half system, if you see, um, like in spin half particle, you have upstate, like which is something given as half or half. And then uh, uh, yeah, and then there is so yeah, and otherwise, like in it is denoted as 1 0. And you have something downstate, half minus half. So, and now if we take like two spin half states, two spin half, then we have more possibilities. Like now we can have this with tensor product with this, which is denoted as this, or this. uh, so then we can have this. So okay, so we see like these are like uh, uh, composite states. So now uh, so this, I mean, earlier, like, I mean, when we were talking about only one spin-off particle which had only upstate and downstate. So these state were only uh, defined, these states were only the available states that define that respective Hilbert space. But now we have a more bigger Hilbert space. So if we say that like one spin half was in H1 Hilbert space, then other would be in the H2 Hilbert space. And when we have this composite states, so they would be I mean, these can be found inside the extended Hilbert space. This, so yeah, so this is the but we have not yet come to what is exactly entanglement. So is uh, mm, yeah, right. So now, like, if you see the state of the combined system is entangled, if it cannot be written as this. So, what it precisely says, if we have something like, as I said, two spin half system and two spin halves quantum system, then we can have states like this, or this, and this, or this. So essentially, so uh, this statement tells that this cannot be your these are not entangled states. These are just composite quantum states. These are not entangled states. So what can be entangled states? If we take some specific linear combination of this states, so these states are sometimes also known as product states. So these are product states. So if we take the linear combination of these product states, then there will be and there then there will be a new linear combination state, which we can call that as entangled state. So this state which you see here, uh, this is something also sometimes known as EPR state. Maybe we'll talk about maybe coming on few more slides. So this is an entangled state. Right. So this is something can be written as okay. And something very interesting about these entangled states are like there are measurements. If we make like measurement on this entangled states, like for example, if I do measurement, what does it mean? It means just let me create some space. Uh, Measurements on entangled state. So by measurements, like we mean it means like by measurements it means like we have to operate uh, like uh, operate some physical observables. So uh, if we measure uh, uh, if we measure entangled states, uh, then it means that like let's say uh, sigma x means we are measuring the or let's say sigma z. We are basically measuring the I mean the spin operator on the entangled state, and the entangled state is, let's say, this is our entangled state, this psi. So if we are measuring this entangled state on sigma z, so it means that like sigma z on psi. So it does that sigma z will operate on this whole thing. Uh, uh, so if you see that like there is only one, like how can I operate this on this? uh, I can like for example, what I mean to say here is on there is only one operator, but there are two states. So I can, using one operator, I can only measure one state only. So there are two states here, but one operator. So if I write this, it eventually means I'm operating basically sigma z cross identity operator on this. So this is what it means if I do operation on this. Then it will give me, like, suppose like when it is very obvious that like from our previous understanding that whenever we operate something on a linear combination of state, so depending upon probability we'll get the outcome, will get one specific outcome. So that is the collapse of a that is like the collapsing to a single state. So which we have seen or discussed many times before. So whenever we measure some operator on a um, linear combination state in quantum mechanics. So suppose if we upon measuring sigma z, So there are let's say if I do this measurement, so I would either get there is half of the chance that I will get this or this, like and you remember that sigma z when operates on this, it gives plus uh, upstate, so there will be some factor of h bar by 2, which I'm not writing it down. So and it would give this if sigma z operates on the downstate. So since this is a linear combination of state, and let's say upon measuring we got the first state, and but still if we see that, like uh, I have measured only sigma z only on the this one, so it will basically give me 1 over square root 2 uh, 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 plus this and cross product with down. So it tells that, like, I have not measured the second spin state which is here, but it is obvious that, like, if I find upon measuring sigma z with this, it will without measuring it will tell me that, like, what would be the measurement of its other pair, which was together with this. So I can say that it will be obviously the down state. So so in nutshell, what I mean to say that in entangled states, so in entangled states, only one measurement is sufficient to know the outcome of of both the pairs. So if I would have like upon measuring sigma z on psi, if I would have got this state, then obviously sigma z would have acted on this one. I would have got this, and then I can confirm without measuring the this one, this other spin state. I would just guess it that it would be upstate, and it will be obviously upstate because this entire thing is prepared as some entangled state. So so yeah, so like we'll see more on this example like in coming on. So yeah, so did you get the point, or any like confusion, anything? uh, if there's any problem, like anything which I may not able to explain here properly, like any problem?
No, sir.
Okay, yeah, okay, then it's fine. So so now, like, we can see, like, there are a few examples here, like, to understand like how we can represent entangled states. So first let's see that there is this right here. So psi 1 is given something as 1 over square root 2, uh, uh, then upstate with downstate, plus with downstate with upstate, and yeah, and this labels which is given right here a b, so it tells that, like, let's say as I have said that, like, these two independently initially belongs to two different quantum system, but when we bring them together, so they appear as together they appear as some quantum composite system, and so we are denoting let's say the first that first quantum system, that isolated quantum system, is something a, or let's say if we are considering, let's say like there are if we make observations, like this is normally the lingo which is used in quantum information. So the language with which we normally explain all the stuffs here is like we consider two observers which are known by their names Alice and Bob, and and s- they happen to share two quantum like pairs of entangled state, which are so. If I say any like whenever if we denote some this kind of composite system which are in linear combination, then we can consider one of this the first states here that corresponds to or that belongs to Alice measurement or Alice qubit, and this corresponds to Bob's uh, qubit. So yeah, I will come to that. Like let's say we have psi 1 right here. So we have to find out whether this is a entangled state or not. So first we can go to the first idea right here, as I said. So when we want have a entangled state, when we see only just a product state like psi 1 tensor product psi 2. But if we have some linear combination of this product state, then and we won't able to factorize it, or we won't able to simplify it to this, then that will guarantee us that that is a entangled state. So whenever as I said, like individually if we see this product states or these composite states, so they are not entangled states. So they can be only entangled if we have this type of linear combination. So we have to find out that. Uh, okay, so if you see that, like I mean there is I mean there is no way, like for example you see this is purely the spin half state, as I have said you earlier. So this is one of the possibility of writing the total spin half state. Like if you remember, there are like if we have two spin half particle, two spin half system in quantum mechanics. If we take the composite system together, so we have one spin belonging to H1, and we have another spin like belonging to H2, or in this case, as we are denoting with Alice and Bob, let's say this is for A, this is HA, and this is B, and this is HB. So now, when we bring them together, so we have this uh, A tensor product with uh, and and this can also have let's see, so this will also have the other sorry, so this is A, and it can also have the downstate. So so same here as well. So I can have for uh, Bob as well, and this belongs to Hilbert space B. So so then I can have this multiple options right here. So this with this, and so this is something you can write it as this, and same way you can also have this, and but on top of that, like you can also make linear combinations, and one and if you see these like these are not entangled states. But if I make linear combination as this right here, so 1 over square root 2 this Yeah, and also this. So the only difference is the relative sign. So these two are quantum states because now we have a linear combination structure. So that is why we can say that this is a entangled state. Uh, so like we cannot write psi 1 as some phi 1 cross phi 2. So it cannot be written as product state. It cannot be represented as product state. So that is why. Yeah. Is there any
Sir,
question?
I have a doubt.
Yeah.
You have written like you've written some expression and then you've written and then again 1 by root 2 and quantum state.
Yeah. Yeah.
So is it for the like in the question some expression is written? So you have simplified this written this one blue one
Uh,
or what
uh,
does this mean? And like you have written,
uh,
you also not have mentioned A or B there.
what does this A or B says? You are you
No,
asking
no,
about?
I'm not asking that, sir.
Okay, okay.
I am asking why have you written this blue line, 1
Uh,
by root 2 and then quantum state and then
this one.
again you written.
I'm saying that like if you like I'm actually I was maybe like I was explaining these things right here. Maybe like okay, just give
Yes,
me a
sir, I
uh,
understand those ones.
okay, okay. Let's just give me a moment. So I was telling that let me write this and this right here. Uh, uh, okay, let me put a tick over here and a tick over here. So what I was telling here, so you have two let's say you have one spin half system. So one spin half system in quantum mechanics, it means that you have some spin half quantum particle, and you can define that quantum particle, that spin half particle, using some quantum states which we have studied like very in details, like in your probably in your starting quantum mechanics class of spin systems, so where you have seen exactly how spin off system can be defined by upstate and downstate. So I guess you know this, like a single spin off state quantum system can be denoted by upstate and downstate. That is right. Do you get that right? uh, Suppose if I take another spin-off system, I take two copies of spin-off system. So I have one spin-off system which can be represented by upstate and downstate, and that I'm giving that I'm denoting by, let's say, some index A. For now you can just remember, just note it as A, or maybe we'll talk about we are writing this A and B for two different observers, Alice and Bob. So we'll see. But yeah, one spin half system corresponds to one particular Hilbert space, because these states will certainly span a Hilbert space. This is the abstract mathematical space in which your quantum state lives. And same way, you have another spin-half system, so it will also be in its respective Hilbert space. But when we bring these two spin half system, so we will have like the spin half system. If you see, it can come with this different permutation, this different combination. So like if we bring one spin upstate, so which has upstate and downstate, and the other spin upstate which also has upstate and downstate. So if we take this and this, so we'll get this system over here. So if you take this or this, we'll get this system over here, and if we take this and this, so we'll get this system over here. And if we take the last two pairs of the spin arm, so we get this. Or otherwise we can also get some linear combination. So linear combination from where we will get, like we'll get linear combination from these two states, so which if we take them with a positive sign, we'll get one distinct linear combination. And if we take these two states with a negative sign in between them, so we will get another. Let me, so this, I think, uh, so this is minus, down and up state. So I'll get these two linear combination state. Okay. So and I'm saying that these two linear combination state can only be your entangled state, but not the only the product states. So the point here I am trying to make here is the entangled state is linear combination of product states, not just product state. If you just have a product state, like for example, if psi 1 would have been just simply some phi 1 tensor product phi 2, then it cannot be your uh, entangled state. So
Yeah,
these
I
two.
understand now.
Okay. Yeah. So you got the point. Okay. Okay. So like any other like question you can ask, anything. Likewise, if you like if you were confused with something that I have said here, like please. Okay. So maybe if not, then you can see the other example. So okay. So next we have psi 2. Again, we have to find out whether this is an entangled state or not. So like on our first like glance, if you would see, it obviously gives you an impression that like you have some two different like tensor product states, and they are combined to be written as some kind of linear combination of state, and it gives you an impression that it is indeed a entangled state. Maybe if you would, on your first glimpse, you would find that, but on a proper attention, if you would see, this is not exactly as a I mean, this is not exactly how we define entangled state, how we represent. uh, so so what here you see is basically, so I can write it as psi 2. Let's say if you see the latter state, the second pair of this product states on both the terms are basically common here. So which means uh, I can do this. I have this state plus this tensor product with this. So now, like suppose if I do the tensor product of this state with I mean this state with this and this state with this, I will get the one which is written on the first line. So now the point here is, now this is just some in like you would see here, this is now just some individual quantum state which is in some linear combination. So now I can write it as 1 over square root 2. I can write the entire thing because this comes with there will be some factors, coefficient factors. So if I take this entire thing as something, let's say uh, I can this is generally denoted as this right side arrow cross down arrow. So this psi 2 is basically your this. So it now it now you can say that your psi 2 can be written as some product state phi 1 and phi 2 can be written as some product state. Therefore, it is not an entangled state. Yeah. So, did you got the point here uh, uh, in this representation right here?
Yes, sir.
Okay. Yeah. So likewise, we have a couple of more examples right here. So like if we see this number 3, uh, okay. So if you see this one right here, so again this I3, like it's in proper entangled state, it cannot be factorized, or it cannot be like reduced to some product state like phi 1, phi 2, uh, unlike the previous one. So that is why so psi 3 is is an entangled state. Now for um, now for psi 4, like what you can see here, uh, like for psi 4, if you see, I mean, like in one of the previous example, as I showed, that there is like there were, after extracting out the common state from the tensor product linear combination here, we got in some so we got one type of state right here, which we denoted by with this right arrow. So if we take these two, what I'm saying, if we take uh, this as your 1 over square root 2 up state uh, plus the down state, and if we take the similar linear combination with a negative sign, so then what you can do, you take will take the uh, tensor product of these two, and right after, if you expand it, you will get the exact thing which is given in this expression. So you'll get 1 over square root 2 the whole thing, so you get this and this uh, plus this, or it would be minus. Yeah, again, so this is what you're given in your question, that is your psi 4. So which is not an entangled state, because psi 4 can be written as some phi 1 tensor product with phi 2. So it is not an entangled state. So like everyone got it, like how you can write down all this uh, forms of entangled states. If any problem, you can please let me know here. Okay, if there is no question right here, uh, so then there's just like I'm like we can just briefly just I can highlight what this APR paradox is all about. So yeah, I think you can see even in the lectures it is talked about. So probably we can try to prove this APR paradox and how this APR paradox was resolved. Maybe in some uh, just okay. So yeah, like we'll try to see how this CPA paradox was resolved. The proof, like maybe in some later discussion, like we'll just try to point out what was this uh, I mean the idea was here. So yeah, this is one of the famous or rather infamous story behind this quantum entanglement. So when quantum entanglement was on its I mean like when uh, this new idea was proposed during that time. So there were obviously some people which won't able to appreciate it much in a way how it was defined. So like for example, uh, uh, there were so this paradox is named by those people. So some popular names right here. So this E basically is for Einstein, and this is Podolsky, and this is Rosen. So these are three famous physicists who were not happy about this whole idea about quantum entanglement phenomena. So how it was defined in particular. So and also in other if we see the other whole of quantum mechanics, how people have been discussing about people have been studying these quantum systems, so using the notion of Copenhagen interpretation, and there were also other multiple interpretations as well. So yeah, none of them is something that is controversial to this date, or something that we cannot go to the lab and just prove it right there. So it is just as it is, and we are just performing mathematics, and then we are finding out some results, and there are some key results at the at our entire huge mathematical calculations, and those results something is meaningful, and what we can test it out in the laboratories, and that has made quantum mechanics to stay where it is, and where we understood from that point very exactly, like what we can see the picture, we can imagine the picture in our brain. But other than there are various things which goes inside, like the linear superposition, the collapsing of state, and all these different interpretations. So to substitute those counterintuitive thinking. So these people, uh, Einstein, Podolsky, Rosen, so they try to propose a different way of understanding quantum mechanics, and that is through something known as hidden variable theory. So like they tried to propose something hidden variable theory. So they first were uncomfortable with the notion or the understanding of quantum mechanics was laid out the way it is even today. So they felt something is incomplete, and particularly the instantaneous collapse of the wave function. So something people thought that physically really happens, that will violate the principle of locality, and something even in special relativity. So it is something very well one of the important postulates is that there is no transmission of signal or information instantaneously. Something cannot go beyond the speed of light transmission. So I mean that the transmission speed should be within this speed of light limit. So all these things like where I mean to defend these arguments, so then they try to propose something hidden variable theory. So hidden variable theory, it tells you that like there are some certain variables in the like in quantum dynamics, in quantum mechanical systems, uh, like which we like which we unable to access them, which we unable to know them beforehand when we are looking at a quantum system, and due to which we see that like all we see all kinds of counterintuitive things. So um, like for example I mean uh, like for example uh, tossing of a coin, let's say, like can anybody like just can anybody try to guess here like whether uh, a tossing of a coin, like which it keeps either head or tail, so it is a probabilistic event, or it is a like non or it is a deterministic event. So so what I mean to say, whether you can precisely determine the event of tossing of a coin, or you cannot, or you can determine with it with some 50% certainty and with 50% uncertainty. So so what it is exactly. So uh, so can anyone just anything, whatever comes to your mind? Is it a probabilistic event or not?
Yeah, it is a probabilistic.
Yeah, so okay, so yeah, so this is a probabilistic event, you can say, and you are right, because this is like something if you are given a coin, some unbiased coin, and you are asked to toss it, so you will find that half of the time you will be correct and half of the time will be incorrect, and so that makes you say it is a probabilistic event. But there is something like, let's say, if we have all the resources with us, what I mean, if we have all the capability of understanding the every possible sequence of that event, or of that particular tossing of a coin. So let's say if I'm tossing a coin, and I'm tossing it with some like I give some torque on that coin, so I place it on my finger, and I give some torque, and then it goes up till some certain distance, or certain height, and then it stops, its velocity stops, and then it starts like falling down. So if I also measure like how much farther it can go up the air, or I can measure if, let's say, the total air dragging, total air resistance present around me, and then when it falls down to the ground, like if I measure the elasticity of the floor, and the also the type of material the coin and the floor is, and then how much coefficient of restitution it will have, and all sorts of information, if i if I have been provided with, then I can tell you that like with whatever initial condition with which I am tossing the coin, I can guarantee you the outcome. Like uh, if I let's say, if I put the face on with head on my thumb finger, and if I give some torque on it, and it will go up, and when it comes down to the ground, and after some bounces, if it settles to the floor, whatever the outcome it will be, I can guarantee you the outcome if I have given with all this information which I said. And then I can say you that this tossing of a coin is basically a deterministic event. This is no more a probabilistic event, because I have all the power to know every bit of information. So this is what the hidden variable. So hidden variable means there are certain informations that I was missing initially. So that made you to say that this is this event of tossing of a coin is a probabilistic event, because you had no idea like how up it will go in the air, and how much bounces it will have when it falls on the ground, and how much time like it will take to reach the ground from your finger, and yeah, everything what was even your initial taught you, imparted on the coin. So everything, like every bit of information was missing. So those missing bit of information is something was you can think of as hidden variables. So that was like the idea even in quantum mechanics, that people like Einstein, Podolsky, Rosen were proposing that there are certain informations which we are unable to access them. So because of which, we see a lot of counterintuitive outcomes, or the yeah. So so this is like the rough idea I've tried to like give you, but it turns out that there is no after all, like I mean, like after all. So you got what I mean by like hidden variables, like through this tossing of a coin, right? So
Yes, sir. Yes, sir.
yeah. So you were right, like it is indeed a probabilistic event, like unless you don't have any access to various other hidden information. So if you've been given with all those hidden information, you will find that this is a deterministic event. So that is what even Einstein, Podolsky, Rosen claimed. So even quantum mechanics is deterministic uh, at large. I mean, as long we are able to access all the pieces of information. So so after all, but it turns out there are no hidden variables. Uh, so this is actually proved by John Bell by an experiment known as Bell's experiment or something. Even from there is a mathematical proof which we can give it here. So like Bell's inequality. So maybe we'll try to discuss it if there is time here, or maybe in the next discussion also we can do that. So yeah, so Bell's inequality like finally proves that like there are no hidden variable, and whatever we see how quantum mechanics it behaves, and it is what the it is what the entire story is like. There is no hidden variable. So yeah, so and probably like more proof or details you can also find in your discussion, or probably we can also discuss more if there is time. So maybe the idea about hidden variable, I think I'm able to convey you. So if not, please let me know. Like there are like one or two more like important things we can see right here. Um, See, like we can go to the applications, like for example, yeah. So like first we can see dense coding. So these are applications of quantum information, or precisely we'll try to see how the idea of quantum entanglement can be extended to various advantages, like in information technology, or yeah, or in information science. So so yeah, what is this dense coding? Um, so this is about like transmitting more than one classical bit in a single qubit. So it's like like using one qubit, how you can transmit two different classical bits. So it's like using qubits to transmit classical information, and also not just like you, for example, to send one classical bit, you require either like one classical bit is given as like 1 or 0. So yeah. So but if you have qubits like which are entangled, so you can send two classical bits of information at a time. Uh, so if I have a entangled state, let's say entangled state, let's say psi, it can uh, so this is, if I have qubit, and this is classical bits. So I can send 11100111. So I can send like any like four of this information, any one of this four through a single qubit. But earlier, like I used to require one bit to send one classical bit of information, this 1 or 0. So like even in qubits, so suppose if I have something this or this, or even this, so these are not entangled. So even here I can send either 1 or 0, or yeah. So even this will also only uh, send only one piece of information, only one something. Yeah. So so if I have like this means EPR, like which I initially said. So if I have this, like I can send either 1 and 1, 1 and 0, 0 and 1, or 1 and 1. So how this can happen? So we can say, let's say uh, um, this EPR which I am calling here. So this is otherwise can be denoted as something chi minus, like we will see. So is given as 1 over square root 2. So we'll get to the labels A and B, A B minus A and B. So this is only EPR state. So okay, so now what we have here is like okay, so this A and B, as I was telling, so they are Alice and Bob. So uh, you have so you have a entangled state. So this is an entangled state. So this is an entangled state, and initially so uh, Alice, which we label it with A, has one pair of qubit, and Bob has other pair. Uh, not just one pair of qubit, it is one pair of entangled qubit and other pair of entangled qubit. So this is what we will try to exploit. As I said at the beginning, if one of them measures one of the measurement on their respective qubit, so the other one will eventually get to know without measuring it. So that is the catch here. So yeah, so it is like so. When I say Alice has one qubit, it means she would either have this or this, or Bob would have either this or this with him. So yeah, so let's say we'll start with let's say Alice wants to send information to Bob. So first, Alice wants to send this classical information. This one. Since she has qubits, entangled qubits, so she can send 1110 or 01 or 11 rather than just 1 or 0 or 1 something. So that is the advantage that we can have if we use this entangled qubits. So so uh, first, like she uh, doesn't let's say we initially Alice has one pair of entangled qubit, so of this chi minus state. So we have this initial entangled state to be this, and this is also chi minus state. So as I said, like Ellie should have either this or this, or Bob should have either this or this. So first, let's say Alice wants to send this information. So first, Alice needs to do some measurement. Like, let me uh, first Alice has to perform some measurement in order to send particular classical particular classical bit or bits of information to Bob. So first, if it can happen, uh, she doesn't measure her qubit, that entangled qubit which she has it with her. So she doesn't measures anything. uh, and suppose, let's say, if she measures uh, the spin, she measures the spin along x-axis, or I mean the x spin component. Then let's say let me just say spin x component. It means that uh, she acts sigma x on her qubit, on her entangled qubit. So it is, so sigma x if c acts on chi minus. So sigma x, you will see the chi minus has is a linear combination of product states. So means each term has two distinct states. So she can only operate on one which belongs to her, not the Bob one. So if I expand, so chi minus has this Alice and Bob, and plus Alice's one and then Bob's one. So and we have a 1 over square root. So she can measure. So she can operate sigma x. So when we say she measures her qubit, which means she is acting the sigma x on the entangled qubit chi minus, which she has. So it means that she can only able to measure her this state or this one, not the Bob's one. So because Bob has his own qubit with him, so has no access. So Alice has no access to Bob's qubit, so she cannot measure Bob's entangled pair of qubit. So this means sigma x. Let me write a over here, tensor product with identity operator. So this is for Bob. So Bob's qubit will go untouched here. So this operates on the right part. So from here, like what you get, so it's like 1 over square root 2 sigma x acts on this, then cancel product with identity operator on this, then same thing, sigma x acts on this, and so this will be, yeah. So if you see that, like sigma x, this is a Pauli matrix which is given as 0 1 1 0, and as we know that this is given as 1 0. So we are writing in all spin z representation, that z component representation, which we all are familiar with. So the generic Pauli matrices and Pauli algebra we are doing. So if you do this, like if you operate sigma x and upstate, which means you do this matrix multiplication of this and this, so you will get this thing right here. So that means you will have 1 over square root 2. You will get this and this, and if you do sigma x on down, you will get a negative sign. Uh, Uh, so yeah, actually this was negative sign from before, so you won't get any extra negative sign. So the negative sign was there from the initial state itself, because the initial state is this one, chi minus. So that is why chi minus. So yeah, if you do the sigma x on down state, so it will give you the up state. So it's upstate Alice and the upstate Bob. So it is 1 over square root 2. So it will give you something this. Uh, yeah, okay. So let's say it will give you this only. So, and we are writing this whole thing as uh, as something phi minus state. So so yeah. So we have two notation here. One is phi minus, and other we had the one which we started is chi minus. So if we write the other ones, the chi plus would be this. Whatever we wrote for chi minus, there will be one. There will be only positive sign instead of negative one. So it will be up, down, positive, and down, up. So these are just some representation of linear combination state to ease our calculation, to simplify or to identify them properly. So phi plus is 1 over square root 2 upstate upstate plus downstate and downstate, and phi minus is upstate upstate minus downstate downstate. So yeah, so as I said, like yeah, so suppose if so we were in the second step. So if she measures sigma x, so like she gets what, this some phi minus state. If she measures sigma x on chi minus, now like if she does the same thing, let's say uh, Alice x sigma y, then if you see sigma y, if, you can do the same calculation back again. If she operates sigma y on chi minus, that will give minus I overall some, this is like a phase vector with 5 plus, so she will get 5 plus. So sigma y, if I which matrix you have to use, like that, this is your y Pauli matrix, which is 0 minus I and 0. So from here you basically get this overall minus I factor, that is just a phase. And finally there is one more measurement she can do, if L is x sigma z, so that is sigma z on chi minus will give chi plus. So now so after this what what Alice does, so after this after this after either one of observe or measurement, either one of this measurement, Alice sends her her qubit to Bob. So now Bob has two qubits. Bob has two qubits. The one which already he had at the beginning, and now which he got it from the Alice. So now, if now what Bob has to do, so Bob can now Bob has to measure sigma x cross sigma x operator and sigma z sigma z, because now Bob has two operators with him, so it's not he can only able to measure his own initial qubit, but rather he can also able to measure the qubit with which she I mean with which he got it from the Alice. So so because now he is in possession of both the entangled pair of qubits, so he can measure the one initially which Alice had, and the one which he already had from the beginning. So two qubits, like so I mean he can use this tensor product operators and measure it. So uh, so now so we can, so this is also like one exercise which you can do, let's say like calculate the calculate or evaluate Bob's measurements, something. So 1 sigma x cross sigma x on 5 plus or minus, then again we can have sigma z cross sigma z chi plus minus, and then sigma x cross sigma x, chi plus or minus, and we have the last sigma z cross sigma z, phi plus or minus. So if you see the one here, first one, sigma x cross sigma x on phi plus or minus, so it means you have sigma x cross sigma x 1 over square root 2. You have this and this. So this is what we wrote initially. I mean, this is how we represented phi plus and minus. If you see, so there will be like a minus sign right here, like so. So this is phi plus, and if I replace it this one with minus, it will become phi minus. So yeah. So now, yeah. So again, you will see that this will act on this one, and this will act on this one. So the same for the second term. So so you will get, if sigma x acts on the first one, it will give you down state, and again you will get down state for the other one when the other sigma x acts on the other pair, and then uh, if it is yeah. So what you will get here, I'm directly writing it down as this. If it is minus, you get with minus sign, and yeah. So this is what, so this you can write it as plus or minus phi plus minus. uh, okay, so now if you do sigma z, let's say uh, let's say if you do the fourth measurement, like the fourth one, sigma z cross sigma z on phi plus sigma z cross sigma z, phi plus or minus. So you'll get 1 over square root 2 upstate downstate plus minus, sorry, upstate and upstate, this is, and downstate and downstate. So again, sigma z will act on the first one. One sigma z will act on first, and the other will on the second. So so here you will find this will be plus 5 plus minus. So what happens, you can also do the other two cases. So this is just simple as we have seen here, like how like we did it with 5 plus, you can do with for the chi plus and minus. So the same, like the algebra or the computation you have to do here. So uh, I can list it down, the four possibilities. So if sigma x cross sigma x acts on 5 plus minus, it will give you plus minus 5 plus minus, as we have seen this one. And if you do sigma x cross sigma x on chi plus minus, so you can check this one, you will get plus or minus chi plus minus. And if sigma x or sigma z on sigma z on 5 plus minus, as we have seen this one, this will give you plus 5 plus minus, and sigma z, tensor product sigma z chi plus minus will give you minus chi plus minus. So you will get a overall minus sign. So what happens? So uh, so let's say uh, you have um, yeah, okay, yeah. So like now what happens? So these are the, like as we have said, so after Alice send her qubit to Bob, so Bob has to do these two operations, sigma x, or and sigma z on the qubit that Alice sent her. I mean, sent him either one of the four. Like, I mean, Alice. Remember, Alice sent her qubit to Bob only after making one of the measurement. So those measurements we have written it down. So if see, initially both of them had one pair of this chi minus, and then Alice makes this sigma x operation, and after that, so there are four possibilities. So and let's say only one of the possibilities that Alice found out, uh, and she sent that to Bob. Then Bob has two qubits with him initially, which he originally had one pair of entangled qubit, and now he is also in possession of Alice qubit. So let's say if Alice outcome is let's say chi plus, so which means initially Alice and Bob had one pair of chi minus, and then after Alice measurement, which she got to be chi plus, she sent chi plus to Bob. So if let's say uh, case one, if Alice's outcome is uh, chi plus, okay, so then uh, Bob measures. So if Alice's outcome is chi plus, that means Alice, that that is Alice operated sigma z on chi minus, because that only gives like sigma minus. If you measure it by sigma z, that will give you chi plus. So that it means. So if Alice's outcome is sigma plus, sorry, if Alice's outcome is chi plus, which means he has measured sigma z, uh, uh, or let me just give me a moment. Yeah, so if she would have measured sigma x, it would have given 5 minus. But if she measures sigma z, then sigma z on chi minus will give let me just write it down here. Sigma x when x on chi minus, it gave minus 5 minus. If sigma z x on uh, chi minus, it will give chi plus. Okay, so you can check that. uh, then Bob measures. So then after, when she got chi plus, she sent it to Bob. Now Bob has 2 qubits, so Bob measures chi plus through sigma x cross sigma x and sigma z cross sigma z. So if sigma x cross sigma x on chi plus and sigma z cross sigma z on chi plus, so one will give, so as we have listed down the possibility, sigma x cross sigma x on chi plus will give plus chi plus, so it will give plus chi plus, and this will give sigma z on chi plus minus chi plus. So this means, like Bob, has two outcomes, either plus 1 or minus 1. So we can, like, think of it as like 2 bits of classical information has been sent. So after the measurement of Bob, so Bob can receive 2 bits of classical information, like, that is 1 and 0. Like, you can think of plus 1 as 1 and minus 1 as classical 0, which how we denote in classical information. So now, the same thing, if it could have been the other way, the other cases as well. So instead of 1 0, it could have been something as like 0 1. So and that would have been, and that uh, will be in the case if Alice's outcome is 5 minus. Then uh, Bob's outcome could have been, will be, you will see it would be either minus 5 minus after acting by sigma x cross sigma x, and it would have been plus 5 minus after acting sigma z cross sigma z. So it is like minus 1 and plus 1. So it's like, you can think of this as 0 and 1. So same way, like, you can also see the other cases 0 0 and 1 1. So this is how, initially, I mean, they had, I mean, you can see that, like, Alice only sent only 1 qubit to Bob, and eventually, and that qubit was, like, initially happened to be entangled, uh, uh, and after sending 1 qubit, one pair of entangled qubit to Bob, Bob is receiving 2 bits of classical information. So this is what we call it as dense coding. So dense amount of, like, information, like, we are transmitting, so using entangled pairs. So did you got the point? Any problem, any question here? Like, any question you can ask, anything not clear anywhere.
Sir,
uh,
it's bit confusing. I didn't like get the story what you were saying na Alice
yeah,
is give. Yeah, I did not understand properly.
the
Yeah,
whole thing.
yeah, yes, sir.
Okay, like, let me try to explain it in a simple way, if possible for me. Like, just like, cut me through wherever you are not able to understand. So please feel free to, like, cut me in the middle anywhere. Like, there is no point if we can just keep on going forward if you are not getting somewhere at the at some previous step. So okay, so yeah, yeah. Um, so I was telling, like, uh, one of the important application of quantum entanglement is this dense coding. So in dense coding, what we do, like, we can send multiple amount of classical bits, some or in this particular case, like we are using like two quantum state entangled, like this up state and up state down state and all this. So in this entangled state, we can send at least 2 bits of classical information using 1 qubit. So it's like I will send like for example, classically what it means, if I send you some 1 bit of information, it means either I have sent only 1 or 0. It means that like I have sent either 1 or 0, because I have sent only 1 bit. Like I'll like for example, you will say I have only 1 bit of information in my drive. So you have only 1 bit of information, that is either 0 or 1. So but here in dense coding, what we are trying to say, we can send, at least in this case, like in the in the EPR state. So this is the EPR state which we are calling the entangled state. This EPR state, if we have this EPR state, this entangled state, we can send uh, two classical bits, 0 and 1, or 1 and 0, or 1 and 1, or 0 and 0 together, only by sending 1 qubit. So I like for example, I'm sending 1 qubit of information to you, and you are receiving 2 bits of classical information, provided there is a catch, provided that beforehand, before I send you 1 qubit, you should have also 1 qubit with you, and I will also have 1 qubit which happens to be entangled. So like for example, if we say this entangled pair, if we say this entangled pair, I have one pair with me, which would be either upstate or downstate, and you also have the other pair, which would be downstate and upstate. So this is provided. This is the essential condition right here. So now we will start from the beginning. You have one pair of qubit, one entangled pair of qubit, and I have the other pair of entangled qubit. And let's say I will send a qubit to you, which I have with me. Yeah, like I will send that qubit after making some measurement or not. Uh, like I will do some measurement or not, depending on that. After whatever the decision is, uh, whether I measure or not, I will send that. After, let's see, if I measure, after measuring, I will send that qubit to you, and then you will measure the you will also do measurement on that qubit which I will send you, and at the end you get two bits of information, two classical bits of information. So this is the overall idea. Like, did you get the overall idea? Like, I can go step by step. Then next, like
Yes, sir.
yeah,
I get it
yeah. So I have uh,
better than before.
yeah, so I have one qubit. I am trying to send that qubit to you, and after I send that qubit, you will do some measurement, and after doing some measurement, you find 2 bits of classical information out of it, which normally doesn't happen if we do classical communication. Like, if I send you 1 bit, you will get only 1 bit of information. But here in this case, I am sending a 1 qubit, you are getting 2 bits of classical information. So this is the gist right here. And then if I have this chi minus state, initially we have this entangled state. Like, I have one pair with me and the other pair with you. So the first I have to make some decision, like whether I will do some measurement or not. Let's say if I measure uh, uh, what let's say this is the qubit which initially you have and also I have, one pair of them. So qubit, this entangled qubit comprises of two pairs, I mean two qubits. So one of the pair is with me and the other is with you. So whatever my measurement will be on this qubit, it will also inflict your measurement. So this is what entanglement is all about. So yeah, first I have to send you a qubit, my pair of entangled qubit to you, after doing a measurement. Let's say, as I said, I measured sigma z on chi minus. It gives me chi plus, and after I get this chi plus, I send this chi plus to you. I send this chi plus to you, and then you make uh, 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 this observation, or it means you make these two measurement. One is this sigma x cross sigma x, and sigma z cross sigma z. Why you will do this sigma x cross sigma x? Like, because I did only sigma x measurement, or either sigma z measurement. Like, it's not like I have not done sigma z cross sigma z, or sigma x cross sigma x, because I only had one qubit, one pair of qubit. But now, after I sent my qubit to you, you have two pairs of qubit. So that is why you will measure the one which has the one which I sent with one of the operator, and also you will have the other original qubit with you from the beginning which you had. So that is why you need two sets of operator which are in tensor product. So, and also to extract out uh, classical information, because you will extract out two pieces of classical information, two bits of classical information. So you will need two measurements. So I only made one measurement, and also you will need two measurement, and also in one measurement there should be two sets of operators which are in tensor product. So as I said, I sent you this chi plus after measurement. I initially we both had one pair of chi minus, this entangled pair, and I made this sigma z measurement. I got chi plus, and I sent you this chi plus. And in this chi plus, you again have your bit and my bit. So this is like, let's say this is my bit, and originally you had your bit of entangled pair. Yeah. So as I was telling, you got I sent you chi plus. So I sent you chi plus. So you will measure chi plus. So you measure look at this one. You will measure sigma x cross sigma x on chi plus, and sigma z cross sigma z on chi plus. So you will get plus chi plus and minus chi plus. So you are getting two different outcomes, plus chi plus and minus chi plus. So it's like two different values you are getting, like two different pieces of information. The eigenvalues are plus one and minus one. So it's like in classically we can denote it as one and zero bit. So this is one classical bit and the other classical bit. So you are getting two bits of information from your measurement, uh, just by sending one qubit to you. So I just sent you one qubit, and you able to extract two bits of classical information. So did you get, or somewhere throughout in any step
Yes, sir, I get it now.
you got? Okay. Yeah, that is fine. Okay, if somebody has again, like, if once I can explain it one more time, like somebody missed it or something not clear at any point throughout this discussion, please. Anyone else? Anybody? Uh, there is. Can you please walk through an example scenario using lens? Density matrix approach. You mean like how? Like again, like I mean, yeah. In density matrix also, instead of states, like you could probably use like I mean, instead of this product states, uh, there will be density matrices. Just you can replace them by states by density matrices, and again the definition of the entangled state will go in that lines. So again, you cannot define entangled state using a product density matrices. So it's like you have to like I mean, you need uh, the linear combination. So is this the one you are talking about, or something else? could you tell me exactly what you want to know? So I mean, if you want to know density matrices, it would be the I mean the way how we've been defining using the states here. So you can see the I mean the product. Yeah, there will be trace calculations. So probably maybe I have to go to that prescription. I have to start from the beginning. Maybe I have to. I don't know here how can I say. um, there, yeah, you need this trace calculation. There are partial traces and there are reduced density matrices. So using that you can do that. So I have to maybe do those things again. Probably maybe I can try to make a note on that maybe next time when I discuss density metrics. So I've not talked about any density metrics yet. So okay. So but yeah, anything maybe with whatever we are trying to discuss, any question here or anything you are finding difficult in your assignments as well, you can ask, or anywhere I mean on this topic. So this one is clear, or like or there is some more problem in understanding the point of dense coding. Okay, so if not, then probably we can go to one more important application here. So maybe we'll see if we fall short of time, then we can discuss it next time. So see, the other one is on quantum teleportation. So so now this now what is this quantum teleportation? This is now sending quantum information using classical bits. So this is the reverse of dense coding, which we uh, talked about just now. So it's like reverse of dense coding. So yeah. So now we have uh, now what we are trying to do here. So we, let's say we have a qubit. Let uh, the qubit uh, so let the qubit be psi, which is to be transmitted. So psi is so this psi is given as alpha upstep, plus beta downstairs. So this is the quantum information that we want to send it. And then and also here it is given that if let's say Alice wants to send this quantum information to Bob, again both Alice and Bob has to uh, share an entangled pair of qubits beforehand. So this is again another provided condition. So this is the provided condition even in the before discussion of our dense coding. And again here also they should have this condition that like initially both should have a shared pair of entangled qubit. So again uh, yeah, so now let's say Alice wants to uh, send this site to Bob. Then so one thing very special about this teleportation is that uh, like Alice wants to send this quantum information to Bob, and the interesting part here is like she doesn't have any idea about what this values of alpha and beta could be. So it's like you're sending some information which you have, but you have not seen it. You have no idea about that, but you can send it to your recipient very securely, like without like even knowing it. And Bob can exactly receive that quantum information which Ellie said without being anyone intercepted. So even like no one can able to copy this information. So there is like something like like another important property about this quantum states that uh, no one there is like no cloning theorem. It prevents no it prevents copy of any quantum state. So it's like so yeah, so if Alice has psi, so it cannot be like copied. So it's not like Alice is where if Alice wants to send this psi to Bob, then Bob gets it entirely. So it's not like you are copying Alice is copying this quantum information, and one copy is going to the Bob and one is like returning with the Alice. But it doesn't like happen like that. So it is like it it just transmits from it just transmits from the sender to the recipient. So there is no extra copy that comes in. So yeah, so now how again this should go through. So like I will try to um, yeah, so again um, both will initially both of them has this APR state chi minus. This is again upstate downstate minus downstate upstate. So if Alice wants to send this, so Alice has initially psi tensor product with chi minus. Uh, so now you can evaluate what this would be. So this is like uh, mm, yeah. So you have this. So you can try this exercise here. Uh, you have 1 over square root 2. Yeah. So if you expand this, what you get these three states, because now you have three states. So finally you get something like this. And what else you have to do now? You remember like the states that which we represented earlier: phi plus, phi minus, and chi plus, and chi minus. So using them you can form some linear combinations, like for example, if I do phi plus, if I do phi plus plus phi minus, I would get something, this upstate. And if I do something like chi plus plus chi minus, I would get something uh, upstate with downstate. So yeah, so this will help you to rewrite this entire thing. Like you can check this. I'm writing it down. I'm leaving out the middle steps. So it would be phi plus minus beta up plus alpha down. Then I would get right, plus phi minus beta upstate plus alpha down. And I would get chi plus minus alpha up plus beta down. Then I think I'll have minus chi minus. Okay, so this is what you have. Uh, Let me check the signs properly. Like, yeah. So yeah, this is, I think this is, yeah, this is correct. So yeah, as I said, like Alice wants to send Sai to Bob, and so so Alice initially also had EPR. So I mean the chi minus state. So what now she has to do? She has to like measure sigma x cross sigma x and sigma z cross sigma z, just like how Bob measured in the previous case. The same thing. Now Alice has to measure, and why Alice has to measure sigma x cross sigma x? And again, remember, Alice already had one pair of entangled qubit, and plus the this qubit, the psi, which she wants to send it to Bob. So then she has to do either sigma x cross sigma x. I mean both. She has to measure both sigma x cross sigma x and sigma z cross sigma z. And in doing that, so again you can do similar type of operation as we have seen in the previous case. Like you can check that this is again the same way you will have the that same calculations. So again, like case one, um, like if uh, Alice measures, which means I mean, if the outcome is 5 plus, then um, then Bob has to operate sigma y to get the following. So see, I mean, if Bob operates sigma y on beta up state plus alpha down state, now you will find that this will give you alpha psi, sorry, I psi. So this I psi, now you see that like this is the original piece of quantum information which Alice wants to send to Bob with some phase, but the important part is the psi with which she wanted to communicate has been done successfully. Like you can find that Bob can calculate, Bob after doing this sigma by measurement, he can exactly get psi. So what Alice has to do is like without knowing what is psi, like she has to just find out what her measurement gives. So if her measurement gives 5 plus, then um, yeah, if her measurement gives 5 plus, then she has to just communicate Bob that he has to make an measurement of sigma y to get the uh, uh, quantum information which she wants to communicate. And the same way, like if we there will be other cases. Case 2, if the outcome of Alice measurement is if yeah, if Alice's measurement is 5 minus, then Bob will act sigma x, and that will give psi. And again, you can thoroughly check these cases. If Alice uh, measurement is chi plus, then Bob will act sigma z, which will give again psi. And then so yeah, if Alice measurement is 5 plus, then Bob doesn't has to operate anything. Then Bob doesn't has to measure anything, because it will directly give it will it will directly give minus sign. So yeah, this is the four way. Like I mean, these are the four ways like where Alice can make measurement on her qubit, which is in tensor product with the psi, the information which the psi is the information which she wants to communicate to Bob. And after whatever the measurement she gets, she has to inform it to Bob, and Bob after getting that information, he also has to make one observation or one measurement. And after that measurement, yeah, you will find that information is that that piece of quantum information is transmitted and right at the point after the measurement of Bob, like after Bob's measurement of uh, qubit which Alice sent him. uh, So yeah, so this is how, like, how quantum information can be teleported. So this is what the idea of quantum teleportation is. So, like, again, if I have probably have gone, I have probably rushed through the end. So yeah, so probably something would have missed definitely. So you can let me know if there is. Immediately we can try to clear out if, uh, or if you want to ask maybe later is also fine. But yeah, if there is any immediate question or something, again, not just this one, even in the previous one and also this one particularly, if not, you got it, please let me know, like, again, did you get the idea, like, or okay, like, anyone else, if there is any other issue, like anything, like anything not clear at any step, please let me know. Yeah, please, if there is any question, you can just, uh, like, let me know now. Uh, uh, if not, then probably we can stop here. If you want to ask later, that is also fine. But I hope, like, you are going well through your registered course, like, I mean, this advanced quantum mechanics. So it is already halfway through. So please try to, like, check through all your updates, and probably towards the end you might have to appear for a test as well. So yeah, so you can also, that could help you better if you can able to clear things from now on. So yeah, so I also try to be updated with your assignments as well. So that is mostly going to help you a lot. And yeah, so any other problem, so yeah, please try to let me know. And there's also in the portal, there are a lot of stuffs already, like the the lecture material videos are always, like, I mean, uploaded timely. So I hope you can able to access all of them. um, yeah, so if there's
Hello, sir.
yeah,
Could you share your email ID?
my email id.
Kindly share your email ID.
Okay,
Yes,
so okay, like, I can, I'm writing it down on the message box. You check it. Yeah, so, like, I hope you can get it from the in call messages in here in this. Uh,
yes, sir.
okay,
I received.
okay, okay. Yeah. Okay, so, like, if there's no more question, then probably we can stop here. We can meet, like, again, around this same time next week. So yeah, yeah. Until then, see you again. So yeah, bye.